All right, so we have seen that considering a steam plant, actually, if we are to consider a steam plant, it is something that we just need to know the formulas from the generation of our steam. So if we consider the question that we have here, we are given the conditions that follow on the boiler and on our steam plant, and also the use of our information sheet. The information and also our steam table. I want us to just talk about this before we consider this as a summary of what exactly is happening here. I think we had a lot of questions that we're going to consider, but you see that, okay, what exactly is happening? Remember the concept of our, the condition of the water. So we have the water and steam flow. This is the water and steam flow. So into the economizer at H1, it is entering at temperature T1, where H1 is the enthalpy of water and H2 also we are having the water. This is the economizer. So from the economizer, where is it going? It goes to the evaporator. So this H2 is the entry to the evaporator at a temperature at 0.2. Then from the evaporator, it's either the steam that you're going to have here now, it's wet or it's dry. This is our H3. So H3 can be given as H wet. Remember that can be given as H wet, or it can be given as HG, depending with how you are given the information. Then to the superheater, which means our H4 represents H sup, which is the end top of the superheated steam, which we can find from the formula Hg into Cp for the superheated, in this case T sup minus Ts. I talked about this formula. Or we can have this at a given pressure. This can be found at a given, so it can be found at a given pressure and temperature. They can give you a pressure and temperature, which you can just take your H sup from there. Provided that this is not there, they will give you the information that corresponds to that. All right. Then we talk about the air preheater, which is the part that is affecting our air. So the air preheater, we have got the part that is, as you can see, this is the part of the fuel, air fuel. That's why we talk about air fuel ratio. It's consisting of air fuel at the same time. So that's our airflow in this case. We've got the T in, which is the temperature of air in, and T out. So they're definitely going to have the specific heat capacity of what? The specific heat capacity of the air in that case. Then as we are talking about the fuel, the gases that you're going to have to talk about the temperature, these are dry gases that you're talking about. T1, T2, T3, T4 to the air evaporator, TFG there, the dry gases as they go to the what? To the chimney. So in the chimney there, that is where now you're talking about what? The flue gases. As you can see, this is the part of the fuel, part there, throughout. So you need to understand whatever that you see on this diagram, the flow of each as it goes. But as we can see, that we just have this only part, the chimney and the air preheater, of which we talked about this from other questions. That is the only part that is actually affecting from our N5. But the rest of the things, you can see that, okay, this is one and the same. Okay, let's see our question here. We are given that a boiler plant, all right, so we've got a boiler plant here. In this case, it's burning fuel with a calorific value of 32 megajoules per kilogram. So just write this in kilojoules so that we do not have problems at the end. So this is our calorific value of 32,000 multiplied by 1,000. That will be kilojoules per what? Per kilogram. And generates, all right, so it generates superheated steam at this pressure. So it is got a superheated steam. Let's just check what else do we have in this case. Then if we check here, At the entrance of the superheater, we're given that this steam is dry, 98% dry, meaning to say at the evaporator, at the output of the evaporator. So there's an evaporator there. Then they're talking about the entry of the water and exit to the economizer. So that means this steam plant, it consists of three things: the economizer, the evaporator, and the superheater. Remember, I said this information is very, very important to consider. Which stages are we having? So in terms of the water, which is the steam flow, we've got those three things that are to be considered. All right, so this one is just a repetition, if you can see. So as I said, we've got the economizer according to what we are given there, the evaporator, and also the superheater. So meaning to say the points, it will be 0.1, 0.2, 0.3, and 0.4. I hope this time we understand. So now let us answer as we are filling on that diagram. So they are saying the superheated steam at a pressure of and temperature. That's for the superheated steam. Remember, these 2 kilopascal, if you multiply by 1,000, that will be 3,800 kilopascal. So we have the temperature for the superheated steam. That's P4. All right, so we've got the 0.4 P4 for the superheated steam, which is given as 3,800 kilopascal. And the temperature that is affecting, which is T sup in that case, the temperature for the superheated steam, which is 298 degrees Celsius. But I say this pressure is the same as the pressure that we have, which is our boiler pressure. So that's P3 is also 3,800 kilopascal. All right. So this is what we have from the first part. Then let us consider again what we are given here. Let us consider this part. They are telling us that at the entrance of the superheater, the steam is 98.6 dry, meaning to say at the exit of the boiler, that's we've got the dryness fraction. At the exit of the evaporator, which is the entry of the superheater, it is 98.6%. So that will be 0.986 as a decimal, 0.986. All right, so this is 986, which is your dryness fraction. So you need that. Then the temperature of the feed water is 29, and all right, so this is the entry, and at the exit of the econometer, the feed water is a temperature of 86. So it enters at 29, it is coming out at 86. So that is Tn. Remember, of the economizer, we still have water here. So meaning to say T1, which is for water, which we are given as 29 degrees Celsius, and this is T2 at the exit, that is 86 degrees Celsius. Remember, I said for water, you can find their enthalpies because they represent HF for water. So it means H1 and H2 can be determined from our steam table. At a temperature of 29, the first one is 29, we need HF, which is the enthalpy of water in kilojoules per watt per kilogram. So that is the first one. It was 29. As you can see, 29 is here, straight at 29. We've got what? 121. So the value that is corresponding, which is 129 for what? For HF. So this is 129 kilojoules per kg. All right, 121 kilojoules per kilogram. All right, then H2, in this case, H2 again is for water, but at what? At 86, it is still water. All right, let's go to 86. Under the temperature, we still, remember, this is the column that we want for HF. That's the column that we're gonna use. But under the temperature of 86, and in this column, under the temperature of 86 here, this is our TS, our temperature. Remember, this is the temperature here, and this is our HF, which is 360 kilojoules per kilogram. So we have got HF there. That's 360 kilojoules per watt per kilogram. All right, this is what we have. This is what we have. So this one, yes, we can find H3, but I'm not going to talk about this now. H3, after the evaporator, we know that here we are told that we are given the dryness fraction. So it means the steam is wet. Then H4 represents H soup. In this case, is for the superheated steam. We're going to talk about that if we need it. Let us just fill in. I think I talked about this. Everything is clear there. Then they are saying the economizer absorbs this heat. This is kilojoules per watt per kilogram. Kilojoules per kilogram, not per kilogram steam, not per kilogram of this, just per kilogram. So we've got Q in the economizer here. All right. This is important. Later on, we might need this information because remember, you are the one who is supposed to find this. But this time they are giving you this. Why? Meaning to say there is something that you're supposed to calculate from there. There is something that is hidden from there. We shall see. Then also the other things that we are given. I think these ones we can even take them later on. Let's see which is important here. The specific heat capacity of the superheated steam. This one we need it. So if we are given this, the specific heat capacity of the superheated steam, it means our H soup in this case is gonna be, we are going to use that at the formula. We are not going to take this direct from what? From the formula, from the steam table, which is our superheated steam. Remember, I said there are two ways. They can give you values which are direct, but when it is like this, it means you are going to find your H4, which is your H soup, from that formula of Hg plus Cp into T soup minus Ts. So that will be the formula that you need there. We shall talk about that. Again, they gave us the temperatures at the entry and exit of the air preheater. Remember, we talked about the air preheater that on that diagram. So let us just write about the air preheater aside. So there is an entry and exit there at the air preheater. All right. So what is it that we have there? We are given the temperatures. All right. This is H, the heater. So there we are given the temperature, Tn. So you're going to have T1 on the preheater, which is 26 degrees Celsius. T2, which is 137 degrees Celsius. We are talking about the air. This is the air. So again, there we can see that still on that, they are giving us the air-fuel ratio because we are given total. This is the information about the air. So they are giving us the air-fuel ratio and also all right, this one we shall talk about this, but they give us the heat capacity of air, which is the specific heat capacity of air. So we have got the air-fuel ratio at the air preheater here. So we have got the specific heat capacity of air also here, which is given. This one for air, which is given as 1,005. All right, let us just confirm. Yeah, that's 1,005. All right, this is for air in kilojoules per kg Kelvin. Okay, just leave it like that. Then we also have the air-fuel ratio 18:1, which is our air-fuel ratio because we are talking about the air. So we shall need this ratio maybe to find the mass of air or whatever that we need. But this is mass of air to the mass of what? To the mass of fuel. All right. Then also they gave us something about the chimney in this case, which is the part that I left out here. They are saying the best temperature, which is the temperature of gas at the chimney base, is 177. I told you that at the base of the chimney, that is your T out. And the chimneys, remember, is one that talks about the flue gases. That is why we're also given the specific heat capacity of the flue gases at the chimney also. So the T that we're given is the temperature out. The best temperature, I talked about this, that is the best temperature is the T out of the chimney. All right, so on the chimney, which means we are talking about what? The flue gases there. That's where we are talking about the flue gases. So we are given the temperature of the chimney of the best, which is T out, which is 177. All right, that's 177 degrees Celsius, and also the specific heat capacity of the what? Of the gases, which is the flue gases in this case. All right, let us can just write flue in this case, flue gases, which is remember it's 1.045 kilojoules per kilogram Kelvin. That is what you're given there. We have this information, guys. We are given this. All right. So whenever we are to refer or to talk about the part where the flue gases are needed, that is the most important part. That is where we are going to need this temperature of 177 degrees Celsius. And it's, like I said, this is the inlet. So this is the output, I mean. So what about the inlet? The inlet is the one that is shared by the air preheater. They share the same temperature at the inlet, which is at 26 degrees Celsius. So this is the information that you need. And definitely under this information, maybe we're going to need mass of the flue gases. So with here, let's just write G, like here we can just write G and so forth. So you're going to need the mass of the flue gases. We shall talk about that. In our calculations, we shall talk about that. But for now, let us answer our questions. All right, so the first question that we are given, I think that's the whole information. We took everything. If not, we shall come back and see, but everything is there. So it was to calculate the following by using tables only, which is the steam tables. So the steam tables are the ones that are needed to take every information, the mass of steam generated in kilogram per kilogram fuel. This is not the first time that we are talking about this. We talked about this type of a question whereby this is needed per kilogram fuel, the mass generated per kilogram fuel. How do we determine this, or how are we going to have this? All right. This is the mass. Remember, you're considering the mass of steam to the mass of fuel. Okay. So let us consider this one. That's, you can just consider as 2.1. This is 2.1. So we need the mass of steam to the mass of fuel. And I said, always this you have to find from something that you're given. Like I was talking about previously. Just take a closer. Why are they giving us this? Why are we given Q there for the economizer? Something that you are the one who is supposed to calculate it, but they are giving you this. Why? There is a part that you're going to need it. So if you check that it consists of this formula, remember that I said the heat that you're going to have to the economizer is going to be the mass of steam over the mass of fuel. Then you consider the enthalpies, the economizer, the output, and the input. The exit minus the inlet to the economizer, so it's going to be H2 minus H1. The economizer 0.2, 0.1. So that will be H2 minus H1. So there is nothing new. So this gives us our answer in kilograms per kilogram fuel. So that means in this case, we need this. What are we going to do to find this? We simply have to divide by the bracket of what? H2 minus H1, since we are multiplying. So if we divide by H2 minus H1, we are left with the mass of steam to the mass of fuel, and that is exactly what we need in that case. So that means the mass of steam to the mass of fuel is going to be given as the Q to the, you use what you are given. Sometimes they might give you the Q for the evaporator. It means you're going to use the one for the evaporator, but it will be H3 minus H2. They might give you for the superheater, it will be H4 minus H3. You use the one that you're given. It's not like always they're going to give you the one for the economizer. No, they can give you anything. So that means the mass of steam to the mass of fuel is going to be given as Q economizer to the economizer what do we have? This is 2,188. So we're just simply substituting our values, 2,188 over H2 minus H1. We are substituting our H enthalpies, H2 and H1. Remember from our steam table, we got these values before. So it's 360 minus 121. So this will give us the mass of steam to the mass of fuel, which is per kilogram fuel that is there. So to 3 decimal place, like I said, you can fix your calculator direct to 3 decimal place so that you do not have any stress of rounding off. So that will be per kilogram fuel in this case. All right, so that's the mass of steam to the mass of fuel. So definitely, most cases, we are going to need this. Mass of steam to the mass of fuel. Let us just write it aside. 9,155 kilograms per kilogram fuel. All right, so that we utilize this in our calculations. All right, so let us just see. So as you can see, it was just 2 marks. Yes, it's the formula there. Then you need to manipulate your formula. Those values, you took them before, so it was just straightforward. Then the enthalpy, the specific enthalpy of the generated, steam generated. All right, the specific enthalpy of the steam generated, 3 marks. Meaning to say we're talking about H soup, the steam generated is at the end here. At the end, we're talking about H soup. So like I said before, that H soup can be determined because we are given the specific heat capacity. So that's why we have to use that formula that we wrote before. So we said H soup is going to be Hg plus Cp for the superheated steam into T soup minus Ts for the saturation temperature. At the pressure that we are given, we're going to find these two. Remember, at the pressure of what? 3,800 kilopascal. All right, so this is your N5, this one. This is all your N5, this part, all these formulas, we talked about this. So that's our H soup is going to be Hg at this pressure at 3,800. What will be Ts there? And Hg. All right, so let's check at 3,800. All right, here. Okay, I actually skipped it here. The pressure, remember, we need the pressure here. The pressure, we're going to need Ts and we're going to need Hg at that. So we need go to down here. All right, so let's check 3,000. All right, actually 3,000 CS, not that far. So we can just consider it here. This is our 3,000, 3,800. 3,800. This is the one that is down here. 3,800 down here. All right. So this is our Hg and this is our Ts at this pressure of 3,800. This is our Ts. This is our Hg. So let us substitute this into our formula and find H soup. So we said Hg there, we saw this, guys, it was 2,801 plus the specific heat capacity here is 3,2. Then T soup is the one that we have here, T soup, which is 298. And we saw that Ts, as we took from the table, it was 247,3 degrees Celsius. So that means we have got H soup there. So this is going to give us 2,963,24, which is in kilojoules per watt per kilogram. So that means we've got H soup, which is H4 in this case. All right. So this is how our questions might be given as. You just have to be careful. So like I said, sometimes they do give us this information which is direct, where you do not even need to apply or to use this formula. You take it direct. That one you just have to take it direct from your what? From your steam table. So but as for this one, we needed the formula, so there was no way we needed the formula. And after We just have to apply everything into the formula to calculate our H soup. Okay, let's see. Let's see what are they saying. The next question here. Then on 2.3, the percentage of heat supplied absorbed by the evaporator. The percentage of heat supplied absorbed by the evaporator. So in this type of a heat that when it is given as a percentage, definitely it will be the thermal efficiency. That represents the thermal efficiency. We talked about this type of a question, but the part that is affecting is that, remember I said about the thermal efficiency that it is supposed to be given like this. All right. That's 2.3. So when you're given this percentage of heat that is taken to the evaporator, that they need the thermal efficiency there. And that thermal efficiency is for the evaporator. Remember, the thermal efficiency can be for the whole plant, for the entire plant. Where I said you are going to use the mass of steam over mass of fuel into H last minus H first. Everything over the mass of steam, mass of fuel times the calorific value. But I said here that if we are to consider the evaporator, our last enthalpy at the evaporator, that's H3. We are not going back to the first one here where the economizer is. No. You focus with the points that build up the evaporator. That will be your first. So H first there is your H2. But if it was for the entire plant, it will be H4, not minus H3, but minus H1. The entire plant is from where it ended, from where it started here to where it ended at point 4. The evaporator is starting here, ending here. That's where the evaporator is starting first, last, on the evaporator only. All right, so you have to be very, very careful. So this is supposed to be kilojoules per watt per kilogram. So everything is there. We're just gonna need to substitute to have this as a percentage. Therefore, we need to multiply by what? By 100%. So that's it. So take note of this type of a question. And also I mentioned that the mass of steam to the mass of fuel, this one is already calculated. This is the one that we calculated. So we got this before, which is 9,155 times H3 minus H2. H3, are we having this? We do not have. H3 represents H wet. We calculated H soup, not H3. So we need H3. H2, we have H2, but H3 we do not have. So guys, just like what we did on H4 for the superheated, we need H3 for representing H wet. Remember, we are told, or we are given the dryness fraction. So H3 is equal to H wet. That means, remember that our H wet is equal to what? Our H wet is equal to HF plus X HFG. This is our N5 as it is, where this is at a pressure, at a given pressure of the boiler there, which is at what? At 3,800 kilopascal. So at this pressure, what is HF? So that will be our H wet, which is H3. So remember, we were at 3,800 before. Let me just try and remove this. Wow, no problem. Let's just go there. 3,800 here. We had these values before at 3,800. All right, straight, we are going to have these values. But this time, what we need there is HF and HFG. All right, so this is our HF here. So we need the value that corresponds there to HF, which is this one, to HF, which is this one, at 3,800. Then HFG, which is this one. All right, so these are the values that we need. And these values, they are in kilojoules per watt per kilogram. So we have got HF and HFG there. All right, so that's our HF. It was 1,073. So we are going to have 1,073 plus HX, which is our dryness fraction, that's 0.986 times HFG, which we saw there, it was 1728. So this is going to give us our H3, which will be 2776,808. So this is kilojoules per watt per kilogram. All right. Remember, the question here, we're not asked about this H3, but we need this. So if you had calculated, like if you check other questions, I calculate these values in the first place. That's why I said that. It is because of this. You need these values. So instead of you now to calculate them, because you need to calculate that question, just calculate these values at once, provided that you know the information that the steam there, it's wet, or the steam is dry, everything you know about that. Use that as an advantage. You can calculate all the possible values from H1 up to HF, up to H4. You can have these ones without a person asking you to say, calculate this, you can do that. Then after that, you just have to fill in. All right. So like I said before, that here, the mass of steam over the mass of fuel is substituted. So we need H3, and we calculated our H3. We got 2776,808 minus H2. This is our H2, which is 360. So this is 360 over the calorific value, which is supposed to be in kilojoules per kilogram. That's why I said whenever you're taking this, make sure also you consider the units. So that gave us 32,000 in kilojoules. So this is 32,000. All right, so that's it. The whole of this part, if we multiply it by 100%, we have got the heat that is given as a percentage, that is the thermal efficiency, which is going to be 69.143%, which is 3 decimal places. So they were actually asking us to calculate the thermal efficiency in a hidden way. They're just hiding this. They are just hiding this. So we have to be very, very careful. Very, very careful. But this is the thermal efficiency for what? Evaporator, the heat that is being taken there. The heat absorbed by the evaporator. Take note what they're asking on 2.4. They are asking the same question, but now it's for the whole plant. This one, when they ask like the thermal efficiency is for the whole plant, the entire plant. This is for the entire plant. So the thermal efficiency for the entire plant, it means in this case, we are going to use from our formula. Remember what I said on this formula. All right. This part is the one that is just going to change. You're just going to change 1 or 2 things here. This one. Remember, I said the formula for the thermal efficiency from this formula is given as mass of steam over mass of fuel into H last, the last enthalpy that we have, depending with what you are working with. This time we are working with what? With the entire plant. The whole plant. So for the whole plant, the last H that we see there is which one? The last H that we see there is the one that we are focusing. And what is the last H, which is our H4? So this will be H4 minus the first one. According to the entire plant, to the whole plant, the first enthalpy there is 121. They are not focusing to say it's an evaporator only that you need. No. It is the whole plant. So from there, you can be able to substitute these values. So that is our thermal efficiency, mass of steam to the mass of fuel. We have this 9,155 times H4 minus H1. So H4 is the last one for the superheated steam, which is 2963,24 minus H1, which is the first one here of 121. Then considering our calorific value in what? Kilojoules per this. I talked about this, guys, and we said it's going to be 32,000. We saw this times 100% since this is efficient. That is as a percentage. So there we have got the thermal efficiency for the entire plant, the whole plant at large. So everything was there. Everything we are given. Everything we have. So to 3 decimal places, that was going to be 81.315%. That is our thermal efficiency for the whole plant, for the entire plant. All right, so if we need this, let's just hope we are going to recall. I'm just going to remove this one. Let's see another question. So these are the typical questions. 2.5. On 2.5, they need us to calculate the percentage of heat supplied absorbed by the air evaporator. So take note, is the percent of this, it's efficiency again. But it's the efficiency that is for the air preheater. All right. So how do we find this one now? All right, this one is going to be a little bit different from others because remember the air preheater, we are talking about the air. This is the air that we have there. So the heat is supposed to be Q from the air. From the air, which is, all right, whenever I talk about this part here, let me explain this. When we are saying this is efficiency, when you are talking about the efficiency, remember efficiency is simply what you have out the output over what you have in the input. So it's P out over Pn. So when we are saying mass of this over this, guys, okay, let's see this. Ms over Mf like this into H2 minus H1 like this over the calorific value. I want you to see this here that we have. This is the input that we have, the heat that we have to the evaporator. The calorific is the input. This is the input. So meaning to say, when we are considering output over input, the input that we are considering for the air preheater, we are talking about air. This is the heat that is from the air. So it's going to be Q air over the Qin, which is the calorific value. Remember, our input is the calorific value times 100% efficiency. So whereby this Q for air, the heat that is going to be taken for air is going to be the mass of air, the specific heat capacity of air times the change in temperature. We talked about this. We talked about this formula. Everything over what? The calorific value. That gives us as a percentage, as an efficiency now. So percentage is just like efficiency, output over input. That is the idea there. That is the whole idea. So the question is that, are we having this? If we check about the air preheater, they gave us this, the specific heat capacity of air. Then from the air fuel ratio, I talked about this, that the air fuel ratio, it represents the mass of air to the mass of fuel. So it's 18:1, that is 18 kilograms. They are saying the mass of air per kilogram fuel, it's 18 kilograms per kilogram fuel. That is what they are saying. Per kilogram of the fuel, the mass of air is 18. So be careful, your information, how it is given. So the mass of air is there. Per kilogram fuel, the mass of air is there. So that means we can calculate everything here. So our thermal efficiency, this is for the preheater. That is for the preheater, it's going to be the mass of air, as we saw, it's going to be 18. The specific heat capacity for air, not for any other thing, but the one for air, 1,005. Because there are so many specific heat capacities, but we need for air, 1,005 times the change in temperature, that will be T out minus T in. At the air preheater, we are given T2 and T1, 137 from a temperature of 26. So we're going to subtract 137 minus what? 137 minus 26. So this is the heat that we have in the air. Then the calorific value in kilojoules per kilogram times 100%. Right? Remember this we already have from our information. So that was going to give us the percentage, which is the efficiency in actual sense, 6.275 as a percentage. 6.275 as a percentage. That's it. Just like that. Output over input. So it was all the whole idea throughout. Output over input. All that was the idea throughout. All right. So that was about what? The preheater. The preheater, we are talking about what? The air. The air is the one that we are referring to, or the one that we are talking about there. So if we check, it's like the whole of this part is on efficiencies. Let's see the other question. Why is it like everything is on efficiency? They are saying it's just like that. If you check this one, this question was just about efficiency. Now they're saying the percentage of heat supplied carried away by the flue gases. So again, we are talking about the output. The flue gases, which heat are they carrying? That is the question. So 2.6. So it's going to be the one for the flue gases, which you can just write as NG. So it's the QN out, in this case, remember output over input for the flue gases over QN, which is our calorific value times 100%. Whereby we know that this for the calorific, for the gases at the flue gases at the chimney, we've got, all right, we need mg in this case. All right, mg from this mass of air to the mass of fuel. It follows that mg is the given ratio. Mg is given as Ma plus Mf. Per kilogram of fuel, the mass of air is 18. If the mass of fuel is 1 kilogram, so that means the mass of the flue gases is going to be 19 kilograms per kilogram fuel. So we have got everything, the mass of this, the specific heat capacity, the change in temperature, because there is T out and T in. So we are going to use the same temperature as what we had for air, but this one is just for flue gases, just one and the same formula. So it's going to be the mass of the flue gases, the specific heat capacity, in this case, times the change in temperature. Everything over calorific value times 100%. That's it. So in this case, we have got the one for the flue gases. The mass, we say that's 19 times Cp for the flue gases we are given. All right, remember the mass here we obtained 19. Then Cp for the flue gases is 1.045. That's 1.045. All right, 1.045 times the change in temperature. Definitely that will be T2 minus T1, T out minus T in. And we have all these temperatures. The best temperature, which is our T out at the chimney, this best temperature is your T out. Then T in is that one that we had at the air preheater. The input to the air preheater, which is 26, so it's 177 minus 26. So we are going to subtract T2 minus T1, 177 minus 26. The calorific value does not change. We still have the same 32,000 times 100% as a percentage. So that was the idea in that case. That was the idea of the question. So this is going to give us 9.414%. Just like that. So all these questions, guys, it was just about efficiency, output over input concept. All right, no problem. Let us consider the other question here. What are they saying? Then the last question, actually, they are saying here, the thermal efficiency of the plant. But haven't we calculated this before? We calculated, but they are saying something here. They are saying the thermal efficiency of the plant if the superheater is defective and is removed. The superheater is defective and is removed. It is no longer part of our diagram. This superheater is no longer there. We are no longer having this. It's defective and it's no longer part of our diagram. So that is the case now. So what is going to be the thermal efficiency? Remember what we said before. The thermal efficiency, all right, that's 2.7. All right, remember what I said. The thermal efficiency is simply taken from this, if you're having from the formula MS into H, this is the last one, minus H first, everything over what? All right, over mass of steam times the calorific value. All right. So there is, in this case, I want us to be careful. I want us to be careful. H last minus H first. They are saying for this one, we removed the superheater. So this one is for the entire plant, the whole plant that we're talking about here. But only that the superheater is removed. So for the entire plant, it means our enthalpy that is at the last point, it's H3, and H first, it's H1. Our plant starts here. So it's going to be H3 minus H1. So take note about how this formula is given. So it means our thermal efficiency, in that case, our thermal efficiency is going to be the mass of steam into H3 minus H1. Everything over what? The mass of fuel times the calorific value. Everything has changed. Everything has changed. Because the superheater has been removed. It's no longer there. So the plant, it now ends at 3, H3, where mass of steam, mass of fuel, we talked about this. So here, I'm not going to have a repetition. We talked about this one. So it's just a substitution that is happening here. That is 9,155 times H3 minus H1 now. This is where it is ending at this point, starting at this point. So it's going to be H3 minus H1. Let's subtract. Remember, our H3 is 2,776 minus H1, which is 121. Everything over the calorific value. This, we have used it. This is the mass of steam over the mass of fuel. So we are left only with the calorific value, which is what? 32,000. That was the idea there. We multiply by 100%. So that is going to give us the thermal efficiency if the superheater was being removed. And that was going to give us 75,981%. So that is how your questions can be like. So if we check this question, it was just like efficiency throughout. Efficiency, this, everything, the percentage of this, the percentage of this, the percentage of all those, they are representing thermal efficiencies. These are thermal efficiencies which are just given in disguise. So we have to understand how questions are given. That is the most important part of our Power Machines M6. We need as much revisions and as much question papers to prepare ourselves for the exams that are ahead of time. But for now, that's it. That's what we have from Mason African Motives till we meet again.